Welcome again to magnetostatic fields. This time we will have some practice problem in Biot-Savart law, which is line of uniform current. This is the first problem application on Biot-Savart law. We have a uniform line of current which extends from minus infinity to infinity, and we have current I naught in the direction of k here, and we want to calculate the magnetic field everywhere. The first observation here is about phi. We have phi dash equal to phi. Phi is where I am observing my magnetic field, and phi dash is the point where my current element is located. Why this happen? Because, for example, if I'm looking in a point in the row, in this case we have phi equals 0, and we have z also is equal to 0, and I'll find my point where the element exists 0, 0, and z dash. But if I'm looking to another point here at y-axis, it will have rho, and phi will be 90, and z also equal to 0. But if I look here, we have also 0, this also 90 in this case, and we have again z dash. This means phi is always equal to phi dash, then they cancel each other, and my magnetic field doesn't depend on phi. Second observation is about R itself. When I'm calculating dH1, for example, let's change the current, my R can be analyzed in rho direction and k direction. But if I'm analyzing a similar element but in the negative z axis, here is another element, say dz dash minus dz dash, for example. So what will happen is that my new R here, R2 for example, has a component minus and rho component. So when you multiply, because our original current is in here, moving in this direction, when I make cross product I naught k with R1 and I naught k cross R2, I'll always have k component cancelled, because cross product k with k equals 0. K cross k always equal to 0. So I'll be left with the rho, which when it is multiplied with k, it will bring me with phi. That's why finally I can say that my magnetic field in the direction of phi. Now I apply Biot-Savart law. Then I have I naught dl cross r over 4 by r cubed. My dl here, as we said, is dz dash in the direction of k, and my r, I just subtract these 2 points here. Let's erase whatever here. So I have here rho minus 0, it bring you with rho in the direction of rho. Then we have phi minus phi dash, we said they are equal, so it's 0. Then we have 0 minus z dash, which bring you z dash in the direction of k. If I want to calculate the magnitude, I square every term, so we have root square of rho square plus z dash square. Here I substitute with whatever we have got, and this is the note which we have noted in the previous slide, that when we multiply k by k cross product, this will result in 0. And to identify the remaining cross product, for example, k cross rho, then we are moving clockwise, then it will bring you with positive phi. So once you apply this one, the k component will disappear, and k cross rho will bring you with phi here. Now let's move the constants outside, and also the direction, which doesn't rely on dz. So we have I naught over 4 pi in the phi direction. We have integration from minus infinity to infinity to some function as shown. We have here rho also doesn't depend on z, but we will use it as we see now. So let's make some substitution. Z dash equal to rho times theta. Once we do so, we need to make some observations, like what will be dz dash in this case. Once we differentiate tan alpha, it will bring you secant square alpha, and rho is constant, and then we have the alpha. If we substitute it with minus infinity, we'll get angle as minus pi over 2. If we substitute with infinity, we will get angle as pi over 2. After substitution, the integration reduced to this form. Now we are simplifying the integration. So we will observe that this, we have rho square here. We have rho cube. This will reduce to rho here. We can make some substitution. 1 plus 10 square alpha equal to secant square alpha. So we can substitute with it here. Then 2 cancel with 2. Then you will have secant cube alpha. Then after you divide secant square over secant cube, you will get 1 over secant alpha, which is cosine alpha. Integration of cosine alpha is very simple. You can find it is just sine alpha. And if you substitute like this, you will have sine pi over 2 minus sine minus pi over 2. This will bring you 1 minus minus 1, which is 2. Then whatever here is just 2, which cancel with 4 here, bring you 2. Then finally you can find that h equal to I naught over 2 by rho multiplied by direction rho. Now we can generalize this result. If we have infinite line of current in the direction AI, you have observation vector R, which is perpendicular to this current, so any current in the space. And if you assume you have observation vector R, but in this time you know this is perpendicular, then your resulting magnetic field will be rotating around this line of current. So how to bring the rotation? You just multiply the two vectors by each other. And why we used here unit vector, because this also phi was a unit vector. AR is R divided by its magnitude. This result is very important because we will use in the next problem. Thank you.